Engineering Design Presentation. Team Srijan Electric. Team Srijan Electric is the former students team of PIT Misra. Our goals for powertrain of a vehicle can be summed up as follows: to design a rule-compliant, data-driven, lightweight, reliable electric powertrain for a Formula Student vehicle, smooth power delivery through an efficient motor with a competitive power-to-weight ratio and simpler cooling requirements controlled by a sophisticated, reliable controller which can be easily tuned, a lightweight, efficient battery pack and rule-compliant container with optimum power and energy density and which can power the vehicle for the endurance event in a single charge of end of life cycle long enough to sustain rigorous testing and equipped with an efficient and rule-compliant battery management system which can be easily tuned according to the dynamic components of HV system. The components of HV system include motor, motor controller, battery pack, battery management system, wiring system, and miscellaneous accumulator or the battery pack. For designing the accumulator, we first required energy and power calculations. As we lacked previous drive cycle data, which is a series of data points representing speed of vehicle versus time, we used Optimum Lab to generate drive cycle data through simulation. It uses a quasi-steady state model to generate data and uses a simplified version of vehicle by using 10 most important parameters. In fact, the validations done by Optimum Lab shows the straight speed, coordinating speed, lap time, and energy consumption within 10% of its real values. We use the following methodology: Optimum Lab simulation for drive cycle data, calculation of required wheel torque and speed from total tractive effort, calculation of required motor torque, speed, and power, calculation for battery pack and energy required for one lap, total energy calculation for a given range, validation, and microcycling. This is a schematic representation of our methodology of how we reach from drive cycle data to total battery pack energy. This is the drive cycle data from lap time simulation plotted on the Excel sheet. Next is battery pack energy calculation simulation in Skilab. The total tractive effort consists of three forces: force of acceleration, which is mass of vehicle into its acceleration, then plus aerodynamic force plus rolling friction force. The total tractive effort is then used to calculate the total wheel torque. The wheel torque and wheel speed is required to measure the motor torque and motor speed. And this slide here shows how we reach from motor speed and motor torque to the total energy required. From the simulations, the total energy required to complete the entire endurance event came out to be 3.658 kilowatt hour. In order to compensate for simulation errors and account for energy required the LV system components, we add an additional 20% of estimate energy to the result. The final estimate battery pack energy came out to be 4.39 kilowatt hour. The current capacity of the battery pack was found to be about 61 ampere hour based on motor voltage, and based on the motor datasheet, it was found that the continuous current would be about 200 amperes. Therefore, it was decided that the maximum discharge rate of cells should be greater than 4 coulomb. The electrical sub-team used the above data for cell selection, battery pack configuration, HV component selection, and accumulator design. Cell chemistry. We chose lithium-ion chemistry-based cells due to lithium having higher energy density, higher power density, and longer lifespan. From all the prominent technologies for lithium-ion cells, the final decision matrix was made between LFP and NMC, that is, lithium iron phosphate and lithium nickel manganese cobalt based technologies. Here are the decision metrics for cell type selection and cell shape selection. From the decision metrics, we can clearly see that we selected NMCs for cell type, and for the cell shape, we chose cylindrical cell. In the end, the cells we selected were Westinghouse 08650 cells. They have a nominal voltage of 3.7 volts, a typical capacity of 2600 mAh, cutoff voltage of 2.75 volt, max continuous discharge current of 15,000 mA, standard charge current 520 mA, and max charge current 5200 mA. Battery pack. The accumulator container consists of 480 2.6 ampere hour Westinghouse cells with a maximum and minimum operating voltage limit of 4.2 volts and 2.7 volt respectively. Battery pack consists of 20 cells in series and 24 cells in parallel. The maximum output voltage of the battery pack is 20 into 4.2, that is 84 volts, nominal being 70 volts. As the max continuous discharge current of the single cell is 15 ampere, the max continuous discharge of the accumulator is 360 ampere. Our battery pack consists of 4 segments, each having 5 cells in series and 24 in parallel, and all the segments are connected to each other through maintenance plugs. You can see it in this diagram below. Battery management system. Battery management system selection. We opted for a centralized BMS system over distributed one primarily for 2 reasons. It's easier to install and the overall cost is lower. Regarding the choice of BMS, we had limited options, with prominent ones being Orion BMS2, Lithium Nade Pro, and MK3X8. We selected the Orion BMS2 because it offered all the required features, making the decision straightforward. You can check the decision metrics even below. We selected the 36 cells configuration one Orion BMS because we had 20 cells in series. Supply voltage is 12 volt DC. Supply current active is 250 mA. Operating temperature is -40 to 80 degrees Celsius. Cell voltage measuring range is 0.5 to 4.2 volts, and cell balancing current is less than 200 mA. Working of Orion BMS2. This diagram here gives a schematic representation of the working of Orion 2 BMS. We would also like to highlight that due to our limited experience and expertise, we did not go for any custom-made BMS. The Orion BMS2 gathers data on cell voltages, current, and temperatures for monitoring and decision making. It measures cell voltages every 30 milliseconds, current every 8 milliseconds using a Hall effect sensor, and temperatures using thermistors connected to the main unit. This data helps ensure safe and efficient operation of the battery pack. The Orion BMS can configure the cooling fan to activate at a set temperature using pulse width modulation to control speed. When the battery pack reaches this temperature, the fan turns on at the lowest PWM speed. As the temperature rises, the fan speed increases accordingly. If the temperature drops below the set threshold, the fan turns off. Additionally, the BMS monitors the fan's health and issues fault code if needed. Estimating SOC. The Orion BMS2 calculates the battery pack's state of charge primarily through coulomb counting, but this method has limitations due to the inaccuracies in current sensor, weak or imbalanced cells. To address these issues, the BMS employs a secondary SOC correction algorithm. This algorithm adjusts dynamically by using the open circuit voltage and highest and lowest cells and comparing them to a table of known voltages called SOC correction drift points. These drift points are configured based on the battery profile and are specific to the cell type used. Cell balancing. The Orion BMS2 employs passive balancing using shunt resistors to discharge the high cells up to 200 mA per cell. Safety measures prevent over-discharging during balancing, and the BMS can halt charging when a cell reaches maximum voltage, continuing balancing after charging stop. Expansion module. Orion BMS comes with only 8 thermistor port, which is insufficient for our use, so the BMS can be connected to up to 10 thermistor expansion modules, which measures up to 80 thermistors each, allowing the BMS to measure over 800 temperatures input. So we use a thermistor expansion module to account for all the thermistors required. BMS data logging helps electric vehicle engineers monitor battery health in real time, ensuring safety and optimal performance. It enables predictive maintenance by analyzing historical data to forecast potential issues and extend battery life. Engineers can utilize this data for performance, optimization, anomaly detection, and regularity compliance. Here is a schematic representation of how data logging is done with Orion BMS2. The data logging display module connects to Orion BMS via Canvas, enabling data logging to an onboard SD card and displaying state of charge through an internal LED bar graph. Meanwhile, the Orion BMS Connect's Wi-Fi module facilitates data logging to an SD card and transmits data to the Orion Connect cloud servers via Wi-Fi, enabling remote data access with an internet connection. Here is a schematic representation of discharge enable output flowchart. Here is a flowchart for charge enable output of our Orion BMS. Next is BMS firmware. Our chosen Orion BMS2 comes with its own software called Orion BMS2 Software Utility. It connects to PC using RS232 port. Inside the software, we can monitor various parameters like voltage, current, and temperature of the cells. You can see the user interface of the software in the screenshot below. Next, in this screenshot, we can see various cell parameters available for viewing in the software along with charging settings. Next, in this screenshot, we can see time versus SOC graph. Next are various failure modes in Orion BMS2. Number 1. Voltage failsafe. The BMS cannot accurately determine cell or total pack voltage due to issues like open tap wires or extreme cell voltages. It enters a non-operating failsafe mode. Here, it gradually reduces charge and discharge current limit to prevent further damage. This allows operators time to safely halt operations, crucial in applications like electric vehicles. It's essential to resolve this error before resetting the system or resuming battery use. Next is current sensor failsafe mode. The BMS activates failsafe mode if the current sensor is unplugged, inaccurate, or not configured. Here, the sensor is disabled, reading 0 amps, while voltage-based protections stay active. Coming to the next slide, we have digital on-off or relay failsafe. The relay failsafe activates if a digital output is turned off but current persists beyond 500 milliseconds. All digital relays latch off until reset or power cycled with a diagnostic code stored. This occurs using only if relays are enabled in settings. 1224 volt supply power failsafe. If BMS's input voltage drops below 8 volt for more than 8 seconds, the input power supply failsafe mode activates. It turns off charge, discharge, and safety outputs, sets digital outputs off, and drops charge discharge limit to 0. Diagnostic trouble codes are stored, but normal operations resume once the voltage is restored. Next is internal memory failsafe. In case of internal BMS memory failure, the BMS loads the factory default battery profile with all the inputs and outputs disabled to protect the battery. The diagnostic code indicates this issue. In the next slide, some other common failure modes are given. You can go through these. Thermal management. As lithium-ion batteries and electronic components are sensitive to temperature, thermal management becomes very necessary. As you can clearly see from this table, our motor and motor controller does not require an external cooling, while Orion BMS2 and battery pack does. The decision matrix shows why we chose forced air cooling upon indirect liquid cooling. The reason for choosing forced air cooling was because of its simplicity, even though the disadvantages, forced air cooling was less efficient, but it was very simple from indirect liquid cooling. This flow diagram shows how we selected the fans. The cell operating temperature is between 20 to 60 degrees Celsius. To convert this lumped system into a steady state system, a worst case scenario was assumed. Maximum current is being drawn, and the battery pack, since it, in this case, maximum heat will be produced. The heat generated from single cell came out to be 1.72225 watt. From a segment came out to be 206.67 watt. We used the following method of approach to select the inlet velocity, which came out to be in between range 2 meter per second to 5 meter per second. We chose 4 meter per second to get the desired output. Assumptions were steady state condition exists. Heat generated at the core of the cell appears at the surface. The same process was repeated for second segment, taking the exit temperature for first segment as the inlet temperature of the second segment. The heat transfer rate came out to be 76.297 watts. Heat transfer rate was greater than heat generation rate, so a cooling velocity 4 meter per second is sufficient to cool the cells. When choosing the type of fan, we chose an axial fan since centrifugal fans have low flow rate and are also very bulky as compared to axial fans. We have 2 fan configuration, 2 80 mm fans and 3 60 mm fans. Choose 3 fan configuration for better cooling. Here are pressure drop calculation and system impedance curves. The operating CFM comes out to 24.7. This is the datasheet of the fan that we selected for our cooling of the BMS. Sorry, the accumulator. As the BMS was in a container, it required cooling. The heat transfer rate ideal was 70 watt and the actual rate came out to be 65.8 watt, which was very good. We used the following specification fan for cooling. Motor. These are the forces which I've already discussed for total tractive effort. On the following formulas, motor sizing was done and total power of the motor was calculated. We had to choose between 3 types of motor: brush DC, brushless DC motors, and induction motors. We eventually went for brushless DC motors. Decision matrix shows why we selected permanent magnet DC motor. We needed to select a motor which has maximum nominal torque at close proximity with 30 Nm. That's why we chose Srijan 119 RPM DC motor. The following slide shows that the nominal torque for Srijan 119 RPM DC motor is 31.77 Nm. For motor controller, we chose Kelly's programmable motor controller as it provided efficient, smooth, and quiet controls for electric vehicles and industrial motor speed control. The schematic shows the connection of motor controller with the motor. Motor is connected between B plus and M pins. Signal from acceleration pedal position sensor goes to ECU, which generates a 0 to 5 volt pulse with modulated output, which is fed to the motor controller. The motor controller on the basis of this PWM controls the motor. It's a schematic diagram of APPS and ECU connection. As you can see from this diagram, high pulse width means high average voltage, which means high speed of the motor.
So now we will discuss about the drivetrain. Our design goals are summarized as: first, to optimize the final drive ratio; second, to achieve a longitudinal acceleration of 0.2 g; third, simple and ergonomic design. Now, I will discuss about the selection of the optimal differential for our Formula Student car, focusing on balancing performance, efficiency, and practicality. Choosing the right differential affects the weight, torque distribution, performance, traction control, and maintenance. We had 3 options, and thus we had made a table listing the advantages and disadvantages of the same. First was the custom open differential, which was light, simple, and cost effective, but at the same time, it resulted in traction loss while cornering. Second was the automatic torque biasing differential, which required lower maintenance but had a narrower torque lockup range. And finally, the third was the Drexler limited slip differential, which had a wider torque lockup range but had a high cost associated. Thus, a decision matrix was made and points were assigned on performance, cost and maintenance, weight and mount weight and their assemblies. And thus, according to that, the decision matrix Drexler open differential was the best choice for us. Now, the Drexler FSA differential that we use is the version 1. The Drexler LSD is also available in 3 versions, differing only in overall width. The version 1 measures 195 mm, version 2 is 215 mm, and version 3 is 235 mm. Despite these differences, all internal components remain identical across all versions. The unit weighs approximately 2 kilograms. The one key feature of this LSD is its top housing, which can be modified to accommodate different carrier bearing position. This ramp and plate type differential comes equipped with press rings that offer multiple ramp angle configuration, allowing us to fine-tune the locking action to suit various driving conditions. In total, there are 6 internal setup possibilities using the provided ramps. The major components of the Drexler LSD included the differential case, the pinion shaft, the pressure rings, the axle bevel gears, and the clutch plates. As we embarked our journey to manufacture our first electric car, we faced unique challenges that it set apart from our work to combustion vehicles. For our combustion vehicle, the 6-speed gearbox allowed us to maintain a final drive ratio between 2.5 to 3, balancing the torque and top end speed effectively. However, with electric motors offering high maximum torque but lacking a gearbox, we had to opt for a final drive ratio between 3 and 4. The adjustments were crucial for achieving the necessary torque without compromising performance. Moreover, incorporating a gearbox for torque multiplication was not feasible. It would not only affect the top end performance due to the low revving nature of the motor, but also pose packing constraints. Increasing the wheelbase to accommodate a gearbox would negatively impact the vehicle's dynamics. So, we can say for an EV, the final drive ratio was calculated on the basis of autocross and skid pad events. The time, as mentioned, was for autocross was 104 seconds, and for skid pad it was 5.88 seconds. The motor was shortlisted could only provide a maximum continuous torque in the range of 31 to 34 Newton meters. So the following criteria should have been fulfilled for the FDR selection, that is the lap times comparable to the benchmark lap times. The maximum continuous motor torque should be below 30 Nm for the dynamic events except acceleration, and longitudinal acceleration of 0.2 g should be achieved. Initially, the team performed lap simulation on Skylabs for autocross, and the results in the graphs are displayed as below. For FDR3, the completion time was 105 seconds. Same was for 3.3, same was for 3.5, same was for 3.75, and same was for 4. Now, the thing to note was that on analysis of the simulation result, it was found out that though the time was the same in all the 3 cases, the motor torque was below 30 Nm only for final drive ratio of 3.75 and 4. So considering the packing constraint, we decided that we would go with a final drive ratio of 3.75, as it would be very difficult to accommodate a sprocket with the reduction of 4:1. And hence, the number of teeth on the driver sprocket and the driven sprocket were fixed at 13 and 45 respectively. The tension in the chain was coming out to be 2100 newtons. Now, we will come on to the design of the half shafts. The half shaft was fabricated from AISI 4340 steel that are vital in transmitting the torque from the axle stub shaft to the outboard stub shaft. This robust material choice ensures durability and strength under operational stress. At the end of each half shaft, tripod bearing fit with the tulip housing. These bearings are splined to the shafts and securely held in place by 2 external rings. These designs ensure reliable torque transmission and structural integrity. To access potential operational issue, the half shaft are designed to be hollow. These allow us to insert a plastic rod fitted with a spring, which serves as a catering device. This innovative solution effectively prevents knocking during operation, maintaining smooth and stable performance. Now, for the selection of material, again, a decision matrix was made, and finally, it was decided that we would go with AISI 4340. We also had made static and dynamic analysis, torsional analysis. Basically, the maximum torque from the engine was 58.10 Nm. The final drive reduction was 3.769. Also, as the Drexler differential had a maximum torque distribution of 80:20, so the maximum torque on half shaft would be around 118 Nm. Now, we have taken the left half shaft length as 431.8 mm. Outer diameter was 20.32 mm. Inner diameter of the shaft was 12.7 mm. For the right hand shaft, the diameter of the shaft was 20.32 mm. Inner diameter of the shaft was 12.7 mm. Also, the length of the shaft was 482.6 mm. Now, the maximum shear stress generated in the shaft was approximately 130.00 megapascal. Yield strength of AISI 4340 was 710 MPa. Now, with the help of maximum shear stress theory, the maximum permissible stress was found out to be 355 megapascal, and thus the factor of safety that we were getting was 2.73. Also, for the dynamic analysis, we had taken the mean torque on the shaft to be 113.07 Newton meters. Also, the stress amplitude for cycle was 130 megapascal. Now, the endurance limit was calculated with the help of Soderberg lines, and it was the most conservative failure criterion. The stress amplitude mean stress line is present inside the Soderberg lines, so the design was considered as safe, as we can see in the figure. And also, the factor of safety in the dynamic loading was 1.25.
Battery auxiliaries. The first component is fuse. Fuse comes into the picture whenever there is overcurrent. Second component, maintenance plugs. Maintenance plugs is a safety equipment, and it is used to break the battery pack into 4 equal components in series. In the schematic, we can see 5 cells in series and 24 cells in parallel in each section, and all these sections are connected in series using maintenance plugs. Next is high voltage disconnect. HVD is used
whenever we need to quickly disconnect the high voltage system. Next, we can see the physical mounting of the HVD. Next, the cables we use are Oflex FT90CY, and its cross-section area is 50 mm square, and we choose this as our nominal current output from the accumulator was 200 amps. Here are the cable specification table. Here in this slide, we have shown high voltage wiring. Accumulator casing. While designing accumulator, we had a lot of material to consider, such as aluminum, steel, composite materials, plastics, magnesium, and thermal management materials. But we opted for aluminum. We opted for aluminum as it was very affordable, and also the heat dissipating property of aluminum was fantastic. So we opted for aluminum. The dimension therefore required was 529 mm to 324.4 mm to 255 mm. Here we can see a schematic of accumulator. Next up, chargers. The current charger that we use has a charging current of 12 amperes, and the total charging time it takes to fully charge a vehicle is 5 hours and 12 minutes. Next, we have the stable. The AC input supply it takes is 230 volt to 120 volt AC, and the DC output it gives is 72 volts and 12 ampere current, and it has an efficiency of up to 90%, and it charges on constant current, constant voltage with charge termination timer and current threshold. It also has visual indicators of LEDs and also an audio indicator as well. Next, we have the connectors for our high voltage. We have used REMA connectors here as they are voted for 150 volts and 320 amperes.
Low voltage system. Low voltage system consists of all the electronic components which works on 12 volt supply. Architecture of LVS. The entire LVS, except for the IMD, is powered from a DC-DC buck converter. LVS consists of safety circuit, tractor system active light, RTD mode activation circuit, RTD sound circuit, expression control position sensor, ECU, wheel speed sensors, and other sensors, plus the low voltage battery. It is made sure that the current flowing through any component does not exceed the current rating of the device. In circuits where high voltage is measured, we use DC-DC isolators and voltage divider circuits. The following slide consists the schematic of the entire circuitry of a vehicle. In the middle there are AIRs, and to the right of AIRs there is the HV system, while to the left there is the low voltage system. Low voltage battery use a 12 volt rechargeable lead acid battery for powering the IMD. Shutdown circuit. Shutdown circuit consists of GLVMS, inertia switch, BSPD, left, right, cockpit, shutdown buttons, bots, BMS interlock, IMD interlock, HVD, and tractor system master switch. This diagram shows the connections of IMD and BMS interlock. IMD interlock is NMOS, while BMS interlock is PMOS. Safety switches. Safety switches are GLVMS, TSMS, brake control switch, and inertia switch. Following CAD rendering shows the position of these switches. BSPD, the brake system positivity device, opens the shutdown circuit whenever there is hard braking while greater than or equal to 5 kW power is delivered to the motor. This is the image of OEM BSPD that we use as we lack technical knowledge and experience for making a custom BSPD. Tractor system active light. The vehicle includes a single TSL that indicates the TS status. Flashes with a frequency of 3.13 Hz to 5 Hz in red color when the TS is active and gives a continuous green illumination when the TS is inactive. This is the TSL schematic diagram for circuitry of TSL. This CAD rendering shows the mounting of TSL LED with housing when green light is mounted in the cockpit. This is a CAD rendering of low voltage casing of our vehicle. Insulation monitoring device. The insulation monitoring device to be used in the competition is a Bender AI isometer. It is powered by a 12 volt battery, as it should not be powered by system which it monitors. It monitors the isolation between the tractive system and the low voltage system. You can see this schematic. For calculations, the minimum response value for IMD for our vehicle came out to be 42 kilo ohms. We choose the IMD which is available in the market and has a default response value of 100 kilo ohm. We use two normally open type electromechanical relays as AIRs, positive and negative. When open, they isolate the battery pack from the vehicle. CAD rendering shows the placement of AIRs, fuses, and IMDs in the connector container. Hardware packaging, harness, and connectors. Circuit enclosures. All PCBs are housed in durable waterproof plastic enclosures to protect against environmental hazards. The visibility of harness. Harnesses are designed for easy access with modular connectors, allowing for quick disconnection and replacement of individual components. This CAD rendering shows the placement of LV system container on a vehicle. Data logging. We have already discussed the importance of data logging. Performance electronics ECU is used to data log the sensor values by measuring the frequency optical volume of the input waveform. This can be done by using two or four digital input pins of the PE3 and we configuration them to measure the frequency. This is done by going to tuning digital inputs. Data logging can be performed by hovering to data acquisition canvas/setup and control, and the channel can be selected from channel selection. Use accelerator pedals position sensor, brake system pressure sensor, current sensor, a temperature sensor in a vehicle. Thank you.